Well, good afternoon. This is Charles Fowler. This is supposed to be differential equations. I'm sorry, I'm a little late getting started. Uh, my wife was getting ready to go take a walk with the dog. I didn't realize we were just out there talking, enjoying the nice weather. I didn't realize the time had snuck up on me, so sorry about that. But so far, I don't see any students here. Hopefully, some of you will be coming in soon. But because we're already a few minutes late getting started, let's go on and proceed. We're in Chapter 4. That's higher order differential equations. And still in Section 4.1, preliminary theory, linear equations. And we're in 4.1.2. The topic is homogeneous or homogeneous equations. And we're on page 122. That is the green topic right near the center of the page called differential equations, which is what the whole course has been about. Okay? Let's just give you an example here. That's where they seem to start. Let me get my pen set up. And please, if anyone's there, please let me know so I'll know to mark you present, because that's the only way I have to do attendance is whether you show up on the class or not. So, any linear differential equation can be expressed in terms of the D notation. Now, they're into this D notation. It's not necessary, okay? It's just another notation, no better, no worse than dy dx or y prime or anything else. It's just a notation, okay? But they're into it now, so let's talk about it. Here is a differential equation, y double prime plus 5y prime plus 6y is equal to 5x minus 3. Now, I found it sort of interesting they gave you this as the example, because the title of this subsection here is homogeneous or homogeneous equations. And this isn't one. That 5x minus 3 makes it non-homogeneous or non-homogeneous. So, but it's okay. There's nothing wrong with it being there. It's just you have a g of x there that you don't. So, if you wanted to write this in the D notation, the capital D notation, the second derivative means d2y plus 5dy plus 6y is equal to 5x minus 3. Okay? Now, you could pull the d's out if you wanted to. Actually, you're pulling the y's out, and that would give you d2 plus 5d plus 6 times y is equal to 5x minus 3. Now, I said times y. That's not really a times y. That's operating on y. You see, each one of these is operating on y. The d2 takes the second derivative of y. The 5d takes 5 times the first derivative of y. And the 6 just says 6. That is a times, 6 times y. Okay? So that's just an operator. Gives you another way of looking at it. Now, there's a reason they're doing this, but they're not making it at all clear now. But in the long run, it doesn't really matter. I mean, it's just another way to look at it. But technically, we're not really going to use it that much. Okay? You can. If you like using it, you certainly can. It's a legitimate notation. Okay? Now, using the equation 8 above, which defines a linear operator, okay? But again, this is rather bizarre. You would have to actually say, then let, and I don't see that they do this step. Let L of y equal d2 plus 5d plus 6, or is it minus 6? Plus 6 is Yeah. Okay. And my pen started doing this last class, and it just every now and then it'll quit writing. Okay. That's your L of Y. So in other words, your L is this operator here. So what did we do? We took our prime operators, made it into a set of D operators, then took the D operators and made it into an L operator. Okay? Fine. I mean, it just seems like you're going around in circles. And then you could say that L, and by the way, this is all equal to some G of X. Okay? There's someone there. Keiston's there. Welcome. Did you have any trouble getting here? I'm sorry, I can't hear. All right. Oh, and Vincent's here too. Perfect attendance today. As far as I know, they don't have Gunter Peyton back in the class yet, but we have Vincent and Keiston here. I can tell Vincent is on his cell phone, right?
Right.
Yeah, iPhone. I can see that. And Keiston, I haven't seen you yet. I just saw that you were in, so that's good to have you both here. I had already started on page, in Chapter 4, Higher Order Differential Equations, 4.1, Preliminary Theory Linear Equations, 4.1.2, Homogeneous or Homogeneous Equations, page 122, and the subtopic here, almost through with what they call differential equations, which is the whole book. Now, before we get going, how do y'all feel about this? Is this working for you, that we meet at regular class times and go from there? We don't have to, but I figured y'all had set aside the time to be in class anyway. Why not keep these times, otherwise finding times that, there's Keiston, I can see you now. Okay. Take care. And feel like I'm going to move you just a little bit to get into the, as far as I can, so I leave as much white space as possible. Okay. But anyway, are y'all okay with this? The way of doing it? Okay.
Is it still going to be, like, you still going to be posting YouTube videos too, right?
Okay, say that one more time.
I said, are you still going to be posting the YouTube videos?
Oh yeah, I'm also recording it. I don't know if you can see this on the screen, but right down here, you see the YouTube is still running. I mean, I'm recording this. Now, I'll say this. I have a feeling that between PowerPoint, Screencast-O-Matic, and Zoom, my computer's getting a little tired of having to keep up with all these things. So every now and then the pen doesn't work well, or something else that I've never had problems with before is happening. But it seems to manage okay. And then too, I've got a learning curve too. I've learned a few things today that I did that I could have done better. So I'll still be getting a little bit better at this too, maybe. Old dogs, new tricks, they don't go too well. Okay. So now, they also say, claim, whatever, that it's just this week. Of course, next week is spring break. Don't expect to get in a Zoom meeting from me next week. You won't, okay? If something were to come up, I have to communicate with you. I may put something out there on YouTube, but I'm not planning to do that either, okay? Next week is spring break. That's the good news. The bad news is we won't be meeting next week at all, okay? But get over it. Then we come back the following week, and the following week is the first full week of nothing but online classes for the whole school. Now, for some reason, they think we'll be coming back after that, what is it, 3rd of April or something like that. I think it's a Friday, so something like the 6th or whatever the next Monday is. I'm saying don't bank on it, because from what my wife's an infectious disease epidemiologist, she's been following and tracking this disease like crazy, she says we're still on the climb. We are getting more and more cases every day. This is nowhere close to peaking. So I can't even imagine that in less than 2 weeks we're going to be over the hump, or a little over 2 weeks we're going to be over the hump. The hump isn't even going to be here yet. Okay, so I would say prepare to do the rest of the term this way. I'm not even certain we'll be doing summer on campus. We might, but the good news is that everybody seems to have really paid a close attention to it's not what the government's saying. The government's been saying things that are just all over the place. But I think they've been paying attention to the scientists now. And, I mean, people are not going, we're not going to the grocery store. Karen's having them bring ship by here, deliver the packages. She's cleaning the box before it comes in the house. She's opening the box, cleaning all the containers before she puts them on the shelves or in the fridge. She's doing all that kind of stuff. I've been out of the house, but only in our backyard, since this began. We're not going anywhere, and a lot of people are doing that. That's the way to minimize the spread of this disease, including people your age. Don't think just because you're young, just because typically the symptoms aren't as bad, you can't spread it like crazy. And if you have grandparents or older parents or older friends, church members, anything like that, you could be taking it right to them. We're staying home. We're staying right here. We're talking about maybe leaving town to go to Georgia, but she said, don't worry, I'll get the gas, because she's worried about my immune system. So be very diligent in what you're doing. It's not going to eliminate the disease, but it will slow its spread. Ultimately, we're all probably going to get it at some point anyway, but what you don't want to do is be contracting the disease or having your grandparents or somebody contracting the disease when all the hospital beds are full. Then they triage people and they say, no, we can't take another one. You're sicker than they are. Sorry, we can't do it. I don't know. We don't want to get there. And we don't want to get to the point where we don't have enough healthcare workers to take care. So that's my spiel. Be careful. That's all I'm saying. All right. Any questions on anything before we get going? Okay. None? Okay. Then let's go on. I was just talking about this. This is an example they give on page 122. Not really an example, just something they listed under differential equations. They just keep breaking it down. Here was the prime operators, the way we express derivatives there. Then they did the capital D operators there. Then they sort of factor out the capital D's and other things from the Y. It's not really a factorization. It's just an operator. And then they let L represent this thing right here. Let that be the L. And then all you say is L of Y is equal to 0 for the homogeneous case. And this is what the pen's doing. It's not writing sometime, and when I'm not even on the page, it's dragging over. So I don't know why it's doing this. I think it's because there's too much on the system. And so I found out in my last class, if I slow down, the pen does a little bit better. You could say that's equal to 0. That'd be a homogeneous case, or say L. There it just, I don't know, it's nuts. L of Y equal G of X. There's non-homogeneous or homogeneous case. This would be saying the same thing that this says. It's just 2 or 3 operators away. Okay. There's nothing new here. It's just different ways to express it. Okay. Moving on from there, the next thing they talk about is the superposition principle. Now, this is something, right now it seems taken completely out of context and doesn't seem to have any tie to anything else. But it will in the future. So get it. This is called the superposition. the sum or superposition of two or more solutions of a homogeneous, this is homogeneous, linear differential equation is also a solution. So here's what they're saying. Let, and they have a whole bunch of them, y sub 1, y sub 2, y sub 3, dot, dot, dot. It's quit writing. Y sub 3, dot, dot, dot. Okay, I don't know why it won't write. All the way up to y sub k. Okay? These are all solutions of a and again, it's not writing, homogeneous linear different or nth order differential equation. I'm just going to write DE to keep from writing as much. Okay, on some interval I. Okay. Now, just a couple things here. If you have an nth order differential equation, you will have n solutions. You may have more than n, but well, why did they use k in one place and n in the other? Well, okay, k may be something less than n, okay? But these are just a number of solutions of an nth order differential equation on some interval I, okay? If indeed that's the case, that these are all solutions for that, especially as long as k is less than or equal to n, okay, then y is equal to c1 y1 of x. The x isn't writing, okay, plus c2, I have to slow down, y2 of x plus c3 y3 of x plus dot 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 plus c sub k, they're still doing k, y sub k of x. Okay, if each one of those is a solution, then the sum of multiples of those solutions is also a solution. Okay? And here are the c sub i's, okay, as if they didn't have enough subscripts here, where I is going from 1, 2, 3, all the way up to and including k. Again, it's not writing well, are arbitrary constants. The c's here, this is the c. Okay, arbitrary constants. That's also a solution. Now guess what? This just doesn't mean there's k solutions or that there's one solution. Any value c could be multiplied by any of the others. That can be a solution. You have an infinite number of solutions here because you have an infinite number of selections for the c's. Okay? And you have KC's, so you have multiples of infinite, so you might say. It's really not. Okay? But that's what the superposition principle is. If you have one solution, 3 solutions, 7 solutions, whatever, then any linear combination of them will be solutions. Okay? Notice you never raise any of these to powers. Okay? It's always a linear combination. Now, that leads to something else. Okay? 2 corollaries. The first of these says a constant multiple y is equal to c1 times y1 of x of a solution y1 of x of a homogeneous linear equation is also a solution. Now this is just breaking it down. Any one of those terms up there is also a solution. If y1 is a solution, any arbitrary constant times y1 is a solution. Okay? And then any sum of any of those are solutions. Okay? So here's the B. Okay? Actually, the A was a homogeneous or homogeneous. And again, it's not writing. The pen just decides not to write. Okay? Homogeneous linear differential equation, DE, it's going to be easier to write, always possesses the trivial solution y is equal to 0. Always, okay? That's the homogeneous case. Remember, the homogeneous case or homogeneous case is when, I'm going to use the short notation, L of y is equal to 0. Well, certainly, if y is equal to 0, doesn't matter what the linear operator is, that's going, goodness gracious, this thing is driving me nuts. Then the trivial solution will always be a solution. Okay? This is so bizarre how it's doing now. Okay. Any questions on that so far? What I'm going to do, I've got a fairly small desk here, and I'm going to try to scoot my computer over so I can see a little bit better from my text. There's a little bit of glare here. Everybody's here, so I don't need the grade book anymore. By the way, in my last class, all 5 students showed up. Here, both students showed up. Way to go. So here's example 4. All right to erase this? Okay. Here's a function. y1 is equal to x squared. Pretty simple function. Okay? And y2 is equal to x squared log x. Okay. Let's just claim they're both solutions of the homogeneous linear differential equation x cubed y triple prime minus 2x y prime, my nose itches, sorry, plus 4y equals 0. Homogeneous differential equation. Okay? On the interval 0 to infinity. Now, first I want to ask you a dumb question. Why that domain? Why 0 to infinity? Now, this is the values that x can take on. Any ideas? See that log x there? Yeah. X can never be negative. X can never be 0. So therefore, 0 to infinity is the largest domain this could be. It may not be on all this, but it certainly couldn't be any on 0 or negative. So therefore, that's at least a reasonable interval here. Okay? If it had said all real numbers x, I say no, it isn't. Okay? Because you couldn't possibly have a log x as a solution there. Okay. No guarantee this will work, but okay. By the superposition principle, then, here is another solution. One of many. Y is equal to, you tell me. Any ideas? Any C1 times x squared. Know where I'm going here? Plus, still no response, C2 x squared log x. There again. I didn't write it that way. The pen is just not cooperating. Okay? Log x. Okay. If I write slow, it'll do okay. That's also a solution. If these two are solutions, then any linear combination of them is a solution. What do I mean by that? Some arbitrary constant, any real number c you want to choose, times x squared plus any other c that you want to choose, or the same one, times x squared log x, also is guaranteed to be a solution. Okay? Now, I think I left, oh no, I didn't leave it out. What we didn't do is verify this. Do y'all feel like you need to, or are you happy just to keep on trucking? Keep on trucking? Okay. Or you wanted to verify? Which should that mean? Huh?
We can keep going.
Keep going? Okay. It's not too hard to verify that. Your y triple prime, your y1 is going to disappear completely, so that won't be hard. The other one, well, you could play around with it and see. Okay, they didn't tell us to verify it. All right. Here's something else coming up. It's not really an example, but it's something else they're treating almost as if it's one, so I'll write it here. Here's a function, y. This is separate from the previous one, so that's why the line is there, except the pen won't write. Okay, I don't know why it won't write, but it won't write. Okay, y is equal to e to the 7x is a solution, okay, of y double prime minus 9y prime plus 14y is equal to 0. It won't write. 0. Okay. Because the differential equation is linear and homogeneous, that's the 0 there, that makes it homogeneous. The constant multiple, y is equal to, again, it starts right and then picks up. Okay? C e to the 7x is also a solution. Okay? For various values of c, we see that you could have 9 times e to the 7x, 0, that would be fine, negative root 5, e to the 7x. Any real 0 you want to put there will also be a solution. Now, we didn't verify that one either, but it's pretty easy to verify. Y prime would be 7e to the 7x. Y double prime would be 49, isn't it? Yeah. E to the 7x. So y double prime would be 49e to the 7x minus 9 times 7 is minus 63. E to the minus 7x plus 14. 14 plus 49, sure enough, is 63. They add to 0. So putting any c in front of that, 9, 85, root 3, 0, anything, those will all be solutions. Okay? Now, I think we need a new screen for the next part. Any questions so far?
No, sir.
Okay. The next two concepts are basic to the study of linear differential equations and many other things too. In fact, both of you will recognize this because this was essential or basic to the study of linear algebra, which you both have had, okay? And that's the concept of linear dependence and independence. So here's a set of functions. F1 of x, F sub 2 of x, F sub 3 of x. Boy, the pen is doing such weird things. Okay? And it'll go on up to and including, this time it's F sub n of x. They just change their subscripts whenever they want to. It's said to be linearly dependent. Sometimes they start with the independent and then go to dependent. This time they're starting with dependent and go to independent. On an interval I, if there exists so ugly constants C1, C2, C3, comma, dot, 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 all the way up to C sub n is the subscript now. Not all zero. Okay. Such that, I'll just put such that, C1, F1, goodness, this pen is driving me nuts. C1, F1 of x plus C2, F2 of x plus C3, F3 of x plus dot, dot, dot plus C sub n, F sub n of x, okay, if that is equal to 0, okay, for every x in the interval. Every x in the interval I. Okay? Now, what does that mean? That you can come up with some combination of c's. Okay? Now, not with all of them being 0. That would certainly work. But some combination of c's, not all being 0. Some of them could be 0. That's fine. But not all zeros. That you can multiply some c by each of those functions, and the c's are not all 0, and you can come up with a set of c's that by adding all those together, if you get 0, that's a linearly dependent system. Okay? They're linearly dependent functions. Now, what does that mean? That means that one of these functions can be written, maybe more than one, in terms of some combination of the others. Because if that's equal to 0, pick out any one of those functions, except one that you chose the c to be 0, okay? Pick out any one of those functions whose c is not 0, subtract it from both sides, you have c times that from both sides, and now you'll see that that one function can be written in terms of all the others, okay? And some linear combination of all the others. That means that one function is linearly dependent on the others, okay? So that's linear dependence. If a set, on the other hand, this set up here, okay, if that set up there of functions is not linearly dependent, okay, then it's linearly independent. Okay, I'm going to abbreviate it there. Okay, what that means, if you cannot come up with a group of c's, some group of c's, any group of c's, as long as they're not all 0, that you can do a combination of those and get you 0 as an answer. If there's no way to do that, then these functions are linearly independent of each other. The other way of saying that, there is no way that you can separate one of them and put it in terms of all the others. You just can't do it. That means they're linearly independent of one another. Okay? In other words, a set of functions is linearly independent on the interval I if the only constants for which that combination would be 0 is for all the c's to be 0. If that's the only way you can make that happen, then that's a linearly independent set of functions. Okay? And that's the key. Okay? Now, if you just have two functions, it's kind of easy to get them to see this, okay? And this sort of goes back, since both of you have had linear algebra. If you had a 2x2 matrix, remember those? And there's several ways to express linear independence or dependence there. But if one row of that was a multiple of another row, then you're linearly dependent. Okay? But if they were not, if it was a 2x2 and one row was not a multiple of the other, not linearly dependent. They would be linearly independent. Now, it's easy to see on a 2x2. When you get up to 3, oh no, you will not be able to pick them out that easily. But two equations, or two functions, if they're multiples of each other, they're dependent, linearly dependent. Okay. That's what they say in italics is what I just said. This book can say the same thing about 3 or 4 different ways, and it seems like the only intent is just to make it more confusing when it's a really simple concept to begin with. We conclude that a set of two functions, alpha1 and alpha2, is linearly independent when neither function is a constant multiple of the other. Yeah, okay, we said that about 3 different ways now. Here's sort of an example. Alpha1 sine 2x. Alpha2, again, my pen's just not writing. Sine x cosine x. Okay, and it just is not writing. Okay, guess what? They are linearly dependent. How do we know that? Go to your double angle formula. Sine of 2x is exactly twice the sine of x times the cosine of x. So, yeah, F1 is twice F2. So they're linearly dependent on each other. They're multiples of each other. Okay. On the other hand, if your F1 of x was x, the identity function, and F2 of x is absolute value of x, it seems like they are so similar, could they possibly? On the interval minus infinity to infinity. On that interval, no, they're not. Because if you picture it, absolute value x is a v function with the point down at the origin, right? Whereas f1 of x is the identity function, which is the main diagonal function, going up, splitting the first quadrant and the third quadrant completely in two. Now, if you take this, the left half of the absolute value function and multiply it by -1, you would get the identity function. But if you did that to the right half, you would not get the identity function. You would get something else, okay, down in the fourth quadrant. So no, this won't work. If that interval was -infinity to 0, yeah, they're dependent on each other. One's a multiple of the other, -1 times the other. If it was 0 to positive infinity, yep, they're the same functions there, identically the same function. They are dependent. But if you're doing -infinity to infinity, or anything to the left of 0 up to anything to the right of 0, not going to be. Anything to the right, anything to the left, strictly to the right or the left, they will be dependent. Okay. The figure in your book shows that picture of what I was trying to describe. So let's do example 5. Any questions so far? Okay. Don't know that I still got you, but I hope they do. Here's a set of functions. f1 of x. Cosine squared x. Okay. f2 of x. Sine squared x. Here's the third one, f3 of x. Secant squared x. Okay, and here's the fourth thing, f4 of x is tangent squared x. These, they claim here they're linearly dependent on the interval -π12 to π12. Now, anyone want to hazard a guess of why that would be the case? Why did they choose -π12 to π12 as the interval? Don't worry about the linear dependence or independence yet. Just worry about why they chose that interval. What do you reckon? Any ideas? Give you a little hint. Sine and cosine and their squares are defined everywhere. Okay? And they're continuous everywhere. Okay? However, secant and tangent are both defined and continuous only between -π12 and π12. Because both secant squared and tangent squared, both secant and tangent blow up at those half pi's. I mean, they have vertical asymptotes at the half pi's. Completely vertical asymptotes. There's no way those will ever be continuous there. So, yeah, you better have, and that is your limits, -π12 to π12. Okay. Now, the question is, are they linearly, they say they're linearly dependent. That means there is some C1 that you multiply by cosine squared x, plus some C2 that you can multiply by sine squared x, plus some C3 that you can multiply by secant squared x, plus some C4 that you can multiply by tangent squared x, that's going to equal 0. without all four of those c's being 0. Okay. Now, if these were nice little linear functions, x, y, z's, and things like this, that would be really easy to solve for. But as it is, it's not a particularly easy thing to see, unless, of course, when you see all those squares of a trig function, does anything come to mind? Like maybe your Pythagorean identities? Yes, right? Let's see. Can you come up with a Pythagorean identity that relates sine squares and cosine squares? You better be able to. Yeah, sine squared x plus cosine squared x, or cosine squared x plus sine squared, doesn't matter, you know is equal to 1. Okay? Is there something sort of equivalent to that for secants and tangents, or secant squares and tangent squares? Anyone remember it?
1 plus tangent squared equals secant.
1 plus tangent squared? Is that what you said? Say yes.
Yes.
Okay. Is equal to?
Secant squared.
Secant squared, exactly. Now, the thing that's going to help us here, folks, is that those little ones there. In fact, I would say, yeah, it's going to be the ones, but I don't want it to be a 1. I want one of them to be a minus 1. Okay? So what I'm going to do is subtract 1 from both sides of this equation. Is that okay? And also, we're going to subtract the secant squared from both sides of this equation. Okay? Now, what we have now is tangent squared x minus secant squared x. This is so aggravating. Really aggravating, is equal to minus 1. Agreed? Okay? Now, I'm going to do something that's really, you would almost say cheap and dirty here. If I say sine squared x plus cosine squared x, we know that's equal to 1, right? Plus tangent squared x minus secant squared x, we know that's equal to minus 1. And what's 1 minus 1? 0. Guess what I've just done? I've come up with some set of C1, C2, C3, and C4 that makes that equal to 0 for every value x between minus pi halves and pi halves. Because you know sine squared x plus cosine squared x is going to be 1, and tangent squared x minus secant squared x is going to be negative 1. Sum of those is going to be 0, and that's not having any of those coefficients being 0. So the coefficients here, the C1 is equal to 1, and the C2 is equal to 1, and the C4 is equal to 1, and C3 is equal to negative 1. There's a set of C's, not all equal to 0, not even a single one of them equal to 0, that makes that sum equal 0. That means you could take any one of those functions out of that and make it a linear combination of the other functions. For instance, just add secant squared to both sides of the equation. You got secant squared x is equal to sine squared x plus cosine squared x plus tangent squared x. Surprise, surprise. There it is. That's equal to secant squared x. Linear combination of those others. Okay. So that was example 5, bottom of page 123, and it moved on to the top of 124. Yeah, they did the same thing. C1 equals C2 equal 1. C3 is equal to -1, and C4 is also equal to 1. Okay. A set of n functions is linearly dependent on an interval I if at least one of the functions can be expressed as a linear combination of the remaining functions. We've said that about 3 different times. For example, 3 functions, f1, f2, and f3, are linearly dependent on I if at least one of those functions is a linear combination of the other 2. Okay? A set of n functions is linearly independent on I if there is no function. Not a single one of them can be written as a linear combination of the others. So let's get ready for example 6. Okay. Trying to remember, we go to 3:45, right? So we got about 17 minutes. So let's move on from here. Example 6. Here's a set of functions. f1 of x is equal to the square root of x. This pen is doing such strange things, I can't believe it. Okay. I'll write more slowly so the pen can keep up. Okay, that's ugly, but it's there. Oh, square root of x plus 5. It's not writing well. f2 of x is equal to the square root of x plus 5x. f3 of x is equal to x minus 1. And f4 of x is equal to x squared. Okay. They claim that's linearly dependent on the interval 0 to infinity. Now, why do you think they chose that interval? Give you one hint. It's not because of functions 3 and 4. They would be good anywhere. What's different about 1 and 2? They have square roots in them, and a square root you can never take the square root of a negative number. Now you could take the square root of 0, so I think 0 could probably be included there, but they excluded it, and that's fine. No, I'm not upset about that at all. Okay? Now, they just came out of the blue and gave you the answer. On this one, I think I'll do a little bit more than that. Hopefully we won't run out of time. So let's do it. What we're trying to show here is that some C1 times the square root of x, I'm going to multiply it by 5 too, plus 5C1 plus okay, C2 times the square root of x. This is so squirrely, okay, plus 5C2x, so I just multiply C2 times both of those, plus C3x minus C3 plus C4x times x squared is equal to 0. Okay? If we can come up with a set of c's, not all of them being 0, certainly if you put every c equals 0, that would equal 0. No problem there. But if we can come up with a set of c's, not all of them equal 0, that would make that 0, then we've got it done. Okay? Now, let's do it a term at a time. Okay? Number 1, there is only one x squared in there. There is no way to get rid of that x squared term unless C4 is indeed equal to 0. That's got to be. But that's okay. You could even have 3 of them equal to 0. That's fine, as long as the fourth one wasn't. That would be sort of hard to do. But so C4 is going to have to equal 0 for that whole expression to be 0. Now, just noticing something else. The terms with square root of x in them, there's only 2 of those, right? And that tells me that C1 must equal minus of C2, because the only way you can get those square root of x's to get out of there is for those 2 coefficients, one of them be the opposite of the other. So C1 equal minus C2, or this is actually going to be the better way to write that, especially since y'all were in linear algebra. I'm going to erase this and write it this way, that C1 plus C2 has to equal 0. By that, C1 plus C2 has to equal 0. Otherwise, C1 times square root of x plus C2 times square root of x will never equal 0. Okay. Now, there's another issue here, that 5C2 plus C3 must equal 0, because all your x terms have to equal 0. And those are the only 2 x terms you have. And there's one more condition, that 5C1 minus C2 is equal to 0, because your constant terms have to add to be 0. We've already determined C4 has to be 0, because there's no way to get that x term out of there unless C4 was 0. All right, well, what do we have? We have a system of 3 equations with 3 variables. We can do that. And both of you did have linear algebra, right? So let's do it by a matrix, okay? And that would be 1, 1, 0. We only have 3 variables, and that would be 0, okay? We probably can leave off the constant 2. Second is 0, 5, 1, 0. And the third one is 5, minus 1, 0, 0. You buy that?
Yes, sir. Yes.
Okay. Now, what I'm going to do here, remember linear algebra? Minus 5 times row 1 plus row 5 is the new row 5. Okay? So this matrix here becomes, and we really don't need that last column of zeros because they're never going to change. So let's do the rest of it. Okay? The first row stays the same, 1, 1, 0, 0. Second row stays the same for now, 0, 5, 1, 0. The new third row is what?
5 still, right?
5 minus, or minus 5 plus 5 is
Oh, minus 5 is
0, right? Okay. Do the same thing for the next one. Minus 5 minus 1 is minus 6.
Minus 6.
Right? And the third one is 0. 0. Okay? Now, next thing I'm going to do two things at once. I'm going to flip the second and third rows, exchange the second and third row. I'm also going to divide that third row or the new second row by minus 6. So that would give me, I'm not going to change the first row, 1, 1, 0, 0. I don't really need that last one. Okay? And then the new second row is going to be a 0, 1, 0, 0. Okay? And the new third row, having flipped it, is 0, 5, 1, 0. Okay. Now, just a little reminder, what we wanted was 1 in the upper left, 0 below it. We got that. What we want next is for the leading non-zero entry in row 2 to be a 1, and we want it in the second position. We got it. And we want it to be 1, but zeros above and below it. So what are we going to do to the top equation to make that 1 become a 0?
I think you wrote the second row wrong.
What's that?
Because you swap rows 2 and 3, right?
Right.
So,
And I also divided by minus 6.
okay, I'm sorry.
Yeah, I did them both at once just because I didn't want to mess with the minus 6 there. And that's legal in most states. You can divide by a row by any non-zero number. Okay? So if I do minus row 2 plus row 1, make it the new row 1, we have a 1, 0, 0, 0. Right? 0, 1, 0, 0. And then we're going to do minus 5 times row 2, add it to row 3. Okay, and it becomes the new row 3. So it'll be 0, 0, why am I not getting the right answer? I must have done something wrong here. This says the only way to do that is for all of them to be 0. That's not the case. I know that's not the case. I made a mistake somewhere here. Let's see if I can find it. C1 plus C2 has to be 0. All right, let me go back to my original problem, make sure I copied it right. Oh. I see where I messed up, I think. Nope, that's right. Oh, there it is. I'm sure I wrote that as a 3, but it didn't write as a 3. So this is a 3 here. So that's where it messed up. So, yuck. Yeah. Okay. That's a 0. That's a minus 1. Everything else changes. Sorry about that, team. Again, I'm going to blame it on the pen. I don't think I wrote that way. Maybe I did. but I don't think I did. All right. That's the C3 there, not a C2. Okay, C1 minus, again, pen screwing me up here. 5C1, 0, minus 1, 0. Okay. So, minus 5 times row 1 added to row 3 becomes a new row 3. Okay. So that would be a 0. That would be a minus 5. Yeah, this is going to work. I'm almost certain of it. And that's going to be a minus 1 equals 0. Okay? Yeah. Guarantee this is going to work. Okay? What I'm going to do is add the two bottom rows together. And what you get is 1, 1, 0, 0. If my pen was right. Okay. 0, 5, 1, 0. If my pen was right. Okay. Add the bottom two rows together. 0, 0, 0, 0. Okay. Now what does that mean? This is one of those equations that the C3, which is what that stands for, is an arbitrary parameter. Let's call it T. Let C3 equal T. Okay? Then the second row tells us that 5C2 plus T is equal to 0. Okay? In other words, C2 is equal to minus 1/5 T. Sorry. Subtract T from both sides, divide by 5. And then you have C1 plus C2, which is minus 1/5 T is equal to 0. So C1 is equal to minus 1/5 T. All right. There's negative 1/5 T, negative 1/5 T, T. Okay, because I don't like fractions that much. I mean, they're fine, but, you know, they're not my favorite. I'm going to multiply each one of those by either 5 or minus 5. So let's just make that C1 is equal to 1, C2 is equal to 1, and C3 is equal to minus 5. Wait. Okay. I really should have been writing this as T, T, and minus 5, T. Yeah. So pick a T, any T. Don't pick 0. All zeros, we know that one's going to work. But let's do 1, 1, and minus 5. Okay? Let's see if that works. Okay? If you do here, you get root x plus 5 I did something else wrong here. These are opposite each other. One of these is plus and one's minus. C1 is plus. Okay. So I'm going to change again. Make this a minus and make that a plus. Okay. So I'm just going to use 1 minus 1, 5. That's going to be the one I'm going to do. So this will be the 1. This will then be a minus 1. That's going to be a minus root x minus 5x And then the last one is 5 plus 5x minus 5. Okay, let's see what happens. These two add to 0, these two add to 0, and those two add to 0. Sure enough, they all do. Or any other multiple of those. Okay? T minus T, 5T. Pick any T. 17. 17 minus 17, and 5 times 17. That will also make that work. So any combination of those like that will do it. Certainly 0, 0, 0 would, but that's always works. These will work for you. Okay? And the one they chose in the book, why did I go against them? They chose 1. Oh, okay. They wrote one in terms of the other. So let's do what we did there. Well, F2, which is, I'm out of room. Let me, if I could get my pen to come up. Okay, let's eliminate this one and that one. Oh, I don't want to do too much here. Okay. This is taking forever to erase, but it's actually doing better than it has it sometimes. Okay. Whoops, that's not what I wanted. Hit the wrong button. Okay. Now what we said was F1 minus F2 plus 5 F3 is equal to 0. Okay? So we pulled off, or they pulled off, said F2 is equal to F1 plus 5 F3. That's what they claimed. Okay, let's see if that works. Let's take our F1, root 5 plus 5, and then we'll add to that 5x minus 5. 5 times F3. And what do you get there? The 5 and minus 5 goes away, and your F2 is indeed root 5 plus 5x is equal to root 5 plus 5x. Yep. F2 can be written as a linear combination of F1 and F3. 1 and 5. Okay. How are we doing on time? Y'all just let me go over 5 minutes, didn't you? Thank you very much. Okay. Guess what? Today I don't have to worry about going to the Birmingham East Campus. I'm already there. Okay? So I don't have to rush out of here. We will begin next time, middle of page 124. Okay? And we've got, yeah, this is going so slowly. We've got a little bit to do to finish 4.1.2, and then we still got 4.1.3 to go. So we've got a little more time in here, but we will hopefully wrap up 4.1.2 next time. Okay? And then we'll move on from there. I think it'll pick up. Oh, let me see if there's any homework exercises for you. Already we've done 4.1.1, so any of the odds, either 1 or 3, you can do if they're in the back. 5 or 7 if they're in the back. 9 if that's in the back. 11 if that's in the back. 13 if that's in the back. Homogeneous equations, you can now do any of the odds 15 through 21. We haven't talked about Those are linearly independent, so you can do those. We haven't talked about fundamental sets yet, so hold off on that, and we'll pick up on those next time. All right, good deal. Glad you're both here. Don't know if we'll be seeing Peyton. Hopefully we will, but so far I don't think he's back in the class yet, but he's trying to get there. Hopefully he's paid by now, so we'll see. He had paid before, but because he was a no-show, they took him out. They may have refunded his money, so he has to get back in. So whatever, if he can get that done, we'll do it. All right, so I'm going to go on and stop it. Any questions before I do? All right, we'll see you then Monday, a week away. That will be the 30th, I think it is, of March. Regular class time, always. And I'll try to be on time today, on Monday. All right, see you then. Have a good spring break. Be safe, be careful.
You too.
Yeah, thank you.
Don't party too hard.
Oh, I'll try not. Bye-bye.